All right, let's go over the second exam together. And the first question was about the strain gauge. So let's say you're working for Lockheed Martin and you measure the aircraft wing using two strain gauges bonded on the top and the bottom surface of the wing near its root, and a Wheatstone bridge and an amplifier. And just like what we see here, and the wing can be assumed as a cantilever beam that has a dimension like this, and the material properties are provided as below. So the question was, yeah, here we still have 5-volt DC supply applied, 5-volt DC voltage applied, and a nominal value of resistance was 120 ohm, and we had a variable resistor over there. And differential amplifier circuit had a gain of 200 over here, and this is the voltage we are measuring. So the first question here was the actual resistance values of the strain gauge on the top and the bottom. The top here was 122 ohm, and the bottom was 124.4 ohm. And resistor R, this is exactly 120. Then what should value of this variable resistor should be? So this times that, and these two, multiplication of those two need to be equal. So it's 122 times RV is 124.4 times 120, right? So by doing this simple math, you can find RV is 122.36, I believe. Okay, and when you're trying to balance, you are not adding these. It's not addition. Nope, it is multiplication. Right? I also remember some of you try to find an average of these and put over there. That's not the case. So in order to balance a Wheatstone bridge, values cross each other, multiplication of those and these need to be the same. All right? Okay. And the next part was, what's the output voltage V out bar here when the bridge is perfectly balanced? And the answer is 0 volt. That's basically the definition of this circuit being balanced. Okay, so you don't need to even think hard to find this one. And then we assume the Wheatstone bridge is balanced now, and the bridge output after amplification was 5 millivolt when a point load P towards the ground perpendicular to the wing was applied at its tip. So if we had a wing like this, then there was a load P applied like that. All right? So in this case, we would like to find the strain value. And the strain is 2 times delta V over VE. That whole thing is divided by the F, right? And the important thing is the coefficient we have is number 2 because we have 2 Wheatstone bridges applied at the wing. Like for example, we have one applied here and one other one applied there. So this is a half bridge, so we need to have number 2 over there. And the value here is going to be what? It's the voltage. This guy, no. It has to be 5 millivolt, which is 10 to the negative 3, divided by 200. This value needs to be in here. In other words, that's the voltage at this point before being amplified. This is 5 millivolt, and you have 200 times gain, right? Gain was 200 times. So voltage before amplification or right after or between these 2 points from the Wheatstone bridge is what? 5 millivolt divided by 200. So that is going to be in here, and the E is what? It's 5 volt, I believe. Yes, 5 volt DC was applied. So we have 5 volt going in here. And gauge factor is provided as 2. So we have number 2 there. Okay, so if you put all the numbers in there, I believe this is the strain value you obtain, or micro epsilon. You can put it like that as well. Okay, and estimate the resistance change of the strain gauge. So again, the strain is delta R over R. That whole thing is divided by F, right? And the strain we just obtained was this, and delta R is something we don't know, and R is 120 ohm, F is 2. So after you do the math, delta R should be something like 1.2 10 to the negative 3 ohm. It's a very small value. All right? And then the strain, the actual length change in the wing in millimeter, strain is defined by delta L over L, right? And from here we have 5e to the negative 6 is delta L millimeter over the overall length, which is 10 meter. So it's 10 to the 3 millimeter, right? So from here, delta L should be something like 50, 10 to the minus 3, something like that. Okay? So with this strain gauge, the important thing that we want to understand was that equation that I told you. Strain is by definition delta L over L, right? And delta R over R F, that is from the Wheatstone bridge, and we can have F, and the coefficient here depends on whether the Wheatstone bridge is a quarter bridge, a full bridge, or half bridge, right? So you may have 4, 2, or 1 depending on the configuration. And the important thing to note is what? This value is before amplification. You need to find voltage at that point. Okay, so if you know how to use this simple equation, then all these problems should be pretty straightforward. And if the resistance change was 1 ohm, then will be the change in the length of the wing, again in millimeter. So we're using this equation, and this delta R is 1, and R again is 120. F is what? It's 2, right? Then we can get the strain. And what's the strain value? That is delta L over L, isn't it? And L in millimeter we're looking for, and the original length was 10 meter, so 10 to the third millimeter, right? So delta L would be 10 third like that of this part, which is 1 over 120 over 2. So if my math was correct, that would give us something like 41.67 millimeters. Okay? All right. And the next part, from the wing in number 1, to identify the vibration characteristic, you just suddenly remove the point load P. Okay, so here had that load being applied, so it was bent a little bit like this, right? And then you just suddenly let it go. Then it will bounce back and then stop, right? And that's what happened here. And again, the wing is assumed as a cantilever beam. And the first part of this question was to find the effective stiffness value of the wing in kilonewton per meter. So effective stiffness is 3E I over L cubed, right? And 3 times E was given as 125 gigapascal. So it's 125 giga, which is 9. And we need to find the I, which is 112 EH cubed. And the length is 10 meters, so 10 to 3. And the width and the height, the width was 1.5 and height is 0.5. So width is 1.5 and height is 0.5. So if you plug in the numbers and do a little bit of math, then it would have given us something like 5.85 10 to the 6. Okay, and this is in Newton per meter. But it was asking in the unit of kilonewton per meter, so convert it into something like this. All right? Okay, the next part, estimate the natural frequency of the wing in hertz. So natural frequency in hertz is 1 over 2 pi, square root k over m, isn't it? So 1 over 2 pi, you're putting the k, which is this value, is not this guy. It has to be in the unit of Newton and meter. And mass is going to be what? 57 times mass of the beam. This is the effective mass, isn't it? These values are effective values. And what's the mass of the beam? Is given, or not, it's not given. So we can use this density and the volume, just like we did in the lab. So density was 1500 kilogram per meter squared times the volume is 10 times 1.5 times 0.5. So this is the volume. This is what? The density. So we get the mass of the beam. So you can just plug in that number here, do a little bit of math, and it should give us something like 7.4764 hertz. Okay. And then let's move on to the next part. If the vibration recorded from the strain gauge looked like what we see here, then estimate the damping ratio. So damping ratio. So the damping ratio, main light, is 1 over 2 pi, natural log of x1 over x2. Right? The peaks right next to each other. So if the first peak here had an amplitude of 5, second peak had an amplitude of 4. So 1 over 2 pi, natural log of 5 over 4. And if you do the math, it should give us something like this. Right? Okay. And then find the frequency of damped vibration FD. So FD is what? It's Fn times square root this. So if you plug in the number, it should be a little bit smaller than what we had originally, 7.4704, like that. Okay? And find the natural frequency of the wing in hertz when you attach a missile 500 kilogram at the wingtip. And we are assuming this missile has a lump mass attached at the tip. So let's say, again, we have this wing and we have mass attached at the tip like this. Then natural frequency, again, is 1 over 2 pi, square root k effective over m effective, right? And adding this mass does not affect the K effective value. So we're going to have the same value as up here. 5, 10 to the 6 over effective mass is this value, 0.2357 times mass of the beam. That value plus tip mass itself, which is 500 kilogram. Right? Don't have the value of this there, but if all the math was correct, we obtained something like 6.86 hertz, which also kind of makes sense. Originally, we have a frequency that is a little bit higher, 7.4, so it is oscillating a little bit fast compared to a case where you have the mass attached, then it will oscillate a little bit slow. So you only have around 6.8 hertz compared to 7.5 hertz. Okay? So after you do a little bit of these math, I want you to check these, make sure whether they make sense physically. Okay? All right, let's move on. And we also had this bonus there where you need to dampen out the vibration of the wing in the case where no missile was attached as quickly as possible. Then determine the damping constant, C. That was the question here. And note that we're not looking for the damping ratio, but damping constant. So first thing we need to note that your damping constant has to be same as C critical, so that it will be a case where that is called critically damped. Right? So find this guy. That is 2 times m times square root K over m. Okay? So you can plug in all these values we obtain from the case where there's no mass attached, like this value and that value. So if you plug in those correctly, we would obtain something like 249, something like this. Second, something like this. Okay? All right, let's move on. The next part here is finding the logic gate expressions from the diagram here. So we would like to express value D, which is at this point, using B and C. So we have what? C is going in, but is negated, and B is going in, right? And they are combined using a AND chip. So B and C dash. That's what we're looking for. And this is going to be your D. And express F using A, B, and C. So for the D, we have that's going into this 4 chip, but before it goes in, it is being negated, right? So we have B and C dash. The whole thing is being negated. That's this part, right? And we have what? We have B and A going into this AND. B, A, combined using an AND. That's going into here. And these two are what? Being combined using an OR. So we are adding those together like this. Okay? That's going to be the expression for F. Okay? And let's move on. The next part here, create a truth table using the logic diagram provided above here, and put the possible combination of the inputs in ascending order. So let's try this thing together. Now A, B, we have C, like that. And 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. 1, 0, 0, 1, 0, 1, 1, 0, 1, 1. So that way we have all possible inputs in an ascending order. It is the smallest number to the largest number, right? And these are the inputs we have. And first we need to find A and B, right? So we try to find A and B. We need to consider these two, right? And because it's and, we need to find a case where we have both of them true. So these two cases are going to be true, and all the others are going to be false. Well, it's a little bit confusing. Let me just draw a line here so that I make sure they're all lined. Okay, so more or less that way we can have these ready, and that was our A and B. So this part is ready, and I need to have B and C dash. So I need to consider B and my C dash. So C dash is going to be 1, 0, 1, 0, 1, 0, 1, 0. So I need to consider these two using a dot, right? So B and C dot can have here, and because it's and, we need to find a case where we have both true. So we have both true here, and that's the only case, isn't it? So this true, false, 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 false. Okay, so there are these, and we just obtained this guy, but we need to negate that one. So B and C dash dash is going to be 1, 1, 0, 1, 1, 1, 1, 1. Right? So from here, we're just flipping those. And eventually, what we're doing is we're combining this one and that one using an OR. So I am combining my AB and this using an OR, isn't it? So if we find a case where we have at least one true, the output is going to be true. So we have a true here, we have a true there, we have a true here, and all of these are true. So 1, 1, 0, 1, 1, 1, 1, 1. That's what we have, isn't it? That's going to be our final answer, F. Okay, does that make sense? And of course, from here, you could have used the Boolean algebra a little bit. This plus B dash plus C. What I mean is I'm putting this inside the parentheses, so this becomes B dash, the dot changes to a plus, and C dash dash, that becomes a C, right? Then we could just find AB, B dash, and C, and add those AB and B dash and just C. So we might not need to do these, but eventually we're going to find the same answer here. So either way, just want you to understand how to find these and create a truth table. Okay, note that please use the ascending order because that way you can minimize any mistakes of missing any possible combination or having duplicates in there. Okay, and the last part is to find a Venn diagram. So we have the universe, we have A, we have group B, we have group C. Okay? And one way, so let's try this thing together. So one way is just try coloring these. So AB is this portion, isn't it? And B dash is not B, so it is outside of B, like that, right? And C is in red, and this is our C. Okay, so the parts yellow, blue, and red are all combined using a plus, right? So if you have a portion that is colored by any of these, yellow, blue, or red, then we're good, right? So in other words, except this portion, it's all being colored. Okay, so that's one way to find the solution. And you can also directly take a look at the truth table. Yeah, and try to think. So let me get rid of these and put these right next to each other. It's easy to view that. Okay, so this input means it's A dash, B dash, C dash, and those are happening all at the same time. So this case is what? A is false, B is false, C is false. What's that situation? It's here, outside of A, B, and C. And what would be this then? It's A, B, and C. They're all true at the same time. And where is that? It's this. Okay? What about this? So color this part, color that part. What's that? 1, 0, 0. So it's A, but it's not B and it's not C. Does that make sense? This is A, B is false, C is false, and they all happen at the same time. Okay? That is this situation, isn't it? It's A, but it is not B, and it's not C either. Okay? So if you think like that, all parts are colored except this case. This case. What case is that? It is A, but it's not B, but it's C. Where is that? Oh, sorry. I just said the opposite. It's not A, but it's B. It's not the C, isn't it? Not A, not C, but it is a B, right? And that is this case, isn't it? And if you see, all the other parts are colored except this portion. So, except this portion, all the other parts are colored. You can consider like that as well by looking at the truth table and trying to find the meaning of that and drawing the Venn diagram. Okay, all right, that's it. Thank you all, and I'll see you guys in class.